morning. So I titled my presentation, Solving Energy Forever for Everyone. And really, that is our goal at Virtus Solis. Our goal is to provide clean, firm, sustainable energy forever. And the sun, 4.5 billion years from now, may not be able to provide that energy anymore, but might as well be forever. But we can do that. We can do that today. The technology is here, and I'm going to tell you how that is important. Now, if we talk about renewable energy, the things that we're not digging out of the ground, they have challenges. This chart shows the history of Germany installing solar power. That's the orange line, installed capacity. And the blue line on the bottom is how much of that installed capacity is being used on a daily basis for the last 20 years. And if anyone is paying attention, about the time that chart goes by, January and February, there isn't very much of that column being generated. That is wintertime. All of us that live in the northern latitudes, it gets cold in the wintertime. And worse yet, it gets cloudy. And that means that you can have solar power that you've installed only generating like 1% to 3% of what you installed. And in fact, the same patterns hold true for natural gas usage in Western Europe. For 10 months of the year, we store all the natural gas that's available and burn it all in just 2 months to stay warm. So we need a solution that is able to provide the energy that we need all the time. Well, that energy is already up there in the sky. We just need to figure a way to get it to the ground. And we call that space-based solar power. It's very simple. You put solar panels in space where there's no weather, there's no day-night cycle, and you get that to the ground. And we'll talk about how we get that to the ground in a little bit, but space solar power as a concept is very straightforward. You just need to get a way to get those solar panels in space. And if you've been paying attention, commercial space launch has been evolving a lot in the last 20 years. In fact, a decade ago, I was at SpaceX developing the Raptor rocket engine that powers the Starship vehicle, which is a new heavy lift launch vehicle. Maybe you've heard about it. It should fly any day now. They're waiting for the FAA to give permission to try again. But that vehicle is designed to be fully reusable and go all the way into orbit and come all the way back and do it a few hundred times before needing to be recycled. Today, SpaceX flies about 16 times the rocket, which is 16 times more than anyone else. And this new rocket, maybe 200, maybe 300, we don't know. But you can get to space very cheaply now. The Falcon Heavy has been around since 2018, and it's very low cost. It's thousands of times lower cost than prior solutions. So you can get things up into space. And what should you do up there? Well, there's going to be 10 billion of us in about 20 years' time, and we all need energy. Pablos described the fact that most of us are in energy poverty globally. The global GDP last year was about $104 trillion, and about 15% of that was primary energy use. That includes all kinds. But the true demand is probably 10x that. And we don't have 10x of the global GDP, so really the only thing you can do is to bring those costs down. Now, the good news is that space solar power as a topic is a generation, it makes the power, and a transmission technology in one. That means that once you can get at it, you can bring it to the ground. And I'm going to tell you about the history of this, because you're going to be amazed at how long we've been talking about this. So this guy is Konstantin Tiarsky. He's a Russian school teacher, prolific inventor. He wrote the rocket equation in 1897. And those of us who develop rockets learned that it's very hard to get off this planet, but it's possible. You need to build a very big rocket that's mostly rocket propellant, fuel and oxidizer, to get off the planet. But he kept going. He described space solar power as a topic, as a technology to power all of us in 1921. So it's 102-year-old as an idea alone. And then another guy, you might have heard of Isaac Asimov, popularized space solar power as a topic in a story called Reason in 1941. And in fact, that became part of the iRobot series, which was very the very first science fiction, kind of, sort of, that was very popular. So it's been around in popular media for a very, very long time. In fact, there's been engineering solutions since 1968. Dr. Peter Glauser, an Englishman working for NASA in the late 60s, actually went through all the engineering necessary to figure out how to build space solar power plants, and he has a patent in the early 70s. So the engineering solutions have been around longer than I have. The problem has been that it was too expensive to do back then. All of the underlying technology you needed, commercial space launch, modern manufacturing, automated manufacturing, and especially the power electronics and what Moore's law has done to a semiconductor manufacturer weren't there yet. But that was a long time ago. This solution is the first one that NASA worked on in the late 70s, and this is called the NASA Reference System. It was a bunch of ex-Apollo engineers. I'm lucky enough to have a father that worked in the Apollo program, so I've been around space for a very long time. But these guys said, hey, you know what? We can do this. We have the technology. We know how to build it. And they spent like on the order of $600 million studying this in the late 70s. So this blue square in the background is the power satellite. It's about 2 gigawatts, about 2 nuclear power plants. But the long axis is 7 kilometers long. It's enormous. It covers all of central London up in space. And they were going to put up 60 of them in a geosynchronous orbit, which means it's sitting over a spot on the ground and beaming power. But in order to make it, they needed to put mines on the moon. They needed to dig materials out of the ground, put them up into space, and put factories up there to turn those raw materials into finished goods and start putting all this together. In fact, they needed space habitats in the lower right, rotating space habitat to put astronauts in to put it all together. And then, worse yet, we needed the space shuttle and its derivatives to get down 1,000 times less cost to orbit than they were operating. And the space shuttle hadn't even flown at this point in time. So NASA went to the US Congress in 1980 and asked for $1 trillion in today's money and said, hey, we'll have the first one operational in 2006. And do you think they got told, go ahead, let's do it? They didn't. They didn't, in fact. And the funny thing is, being an American and talking to my colleagues at NASA, they remember being told no. They remember it so much so that they don't want to see another dime spent on this technology, at least until relatively recently. And it took a friend of a friend who had a conversation with a British business called Reaction Engines, who is developing aerospace planes. A friend of mine named Keith Henson, who is part of what I'll show you on the next slide, asked, hey, what does it take to put up millions of tons into orbit? And he talked to his friends at Reaction Engines, and they said, well, we know we need to build about 20,000 rockets to fly it up there. And we can do that, and we can reuse them, and it'll be low cost. And that was in the early 2000s. And then when the UK decided that they needed to fix their energy, there was something called the Net Zero Initiative. And they went and looked at offshore wind, onshore wind, terrestrial solar, new nuclear power plants, and space solar, which no one had been talking about for about 40 years. And it was because Martin Soltau, who runs another business based here in the UK called Space Solar, which is doing the same thing as we are, had known about this study at Reaction Engines. So all that snowballed into an effort to develop this. And so the Europeans actually are moving faster than us in the US on this topic because they didn't get told no. So I'm going to tell you a little bit more about that. But more importantly, in-space infrastructure is the key to making the circular economy and everything off this planet work. And right now, the communication infrastructure is the only thing we have in orbit today. You might recognize some of this artwork. This was Gerard O'Neill at Princeton in the late 70s. He and his students were trying to imagine what should humanity do? I mean, where should we live? Where should we operate? And they came to the conclusion that we should live and operate off the planet. And there's a lot of us who believe in that vision. We should be able to live on this planet. It's great, but we should also be able to live anywhere else. And we need to figure out how to live up there. And these are renderings of habitats. And the one in the lower left is actually made by a guy named Jeff Bezos. He wants to do the same thing. He's very big a fan of it, but the way these things were going to be built and paid for is building solar power satellites. And in the late 70s, early 80s, it just wasn't commercially viable yet. And one of the big challenges was not only the economics, because the underlying technology wasn't there, but it was in a way. And I'm going to tell you about that in a moment. So my company, Virtus Solis, we have solved the last little remaining element, and that is how to get the energy from orbit to the ground. We're using low-intensity microwaves. In fact, we did a study for NASA to do this on the moon for their very first lunar base a year ago, and this is the winning proposal. They needed to figure out a way, because there's no infrastructure on the moon, to put power plants on the ground and then distribute that energy to all the different end users. So with that, I think we are going to run a video telling you basically at a high level how my system works.
Moore's law and modern manufacture enables in-space infrastructure. Space-based solar power satellites are the key infrastructure for expanding into space. Low Earth orbit is not suitable for solar power satellites, but on-orbit propellant transfer allows access to higher orbits at low marginal cost. Virtus Solis's power satellite constellation is planned for a 12-hour medium Earth orbit called Molnia, which is uncrowded and highly elliptical, spending 11.5 hours of every 12 at 35,000 kilometers above the northern or southern hemisphere. This orbit allows 2 ground stations on opposing sides of the planet to be served sequentially, providing baseload capabilities. The arrays of thin tile satellites are assembled in the final orbit, transported flat-packed in racks for maximum usage of the rocket's payload bays. The assembly robots extract 25,000 satellites and then assemble them into arrays of 100,000 or more. Each autonomous satellite delivers about 1 kilowatt to the ground, and the arrays can scale up to over 20 gigawatts each. As the satellites are interchangeable and cost less than a laptop, servicing amounts to removing and replacing elements of the array. The assembly process is simple. Extract the satellites from the racks and click together like Legos into large circular transmitters of 0.5 to 3 kilometers in diameter. Once a sufficient size, the arrays can transmit power to 1 or more ground stations, and a constellation of 2 or more can provide baseload power to multiple ground stations simultaneously. You can see this constellation of 3 power satellites provides redundant coverage to nearly the entire northern hemisphere. The ground stations are 2 kilometers in diameter and can absorb up to 1.5 gigawatts each, powering 150,000 people, and can be sited and built like conventional solar farms near end users. The launch vehicle can return to the launch site and be reused with only small propellant use. Virtus Solis is Latin for the power of the sun. Virtus is the root of virtue, and as the Romans didn't have a concept of energy as we do, it is better translated as power or kingly authority. This power to change the world aligns with our vision of clean, firm, low-cost, globally available energy. Low-cost energy is the greatest lever for universal prosperity.
So that's all really nice renderings, right? How far away are we from reality to doing all this? Well, the good news, I've already built it. The key element is the proof of concept that we've done is a wireless power transfer system that can operate from orbit, 35,000 kilometers above us, all the way to the ground. And at that altitude, about half the Earth's surface is visible in line of sight. And if you build a transmitter big enough, you can move power wirelessly at very high efficiencies. We're talking high 90s. In fact, we've chosen 10 gigahertz microwaves because it penetrates the atmosphere and weather with almost no loss. We account for about 1.5% to 2% of the total energy that we transmit will be lost in that area. So in order to prove it works, we had to build a demonstrator. In fact, this March of this year, we built the largest wireless power transfer system, the first one to do end-to-end wireless power transfer. We did it over 100 meters on a football pitch. And this is the system that I'm going to show you part of today, and I'll show you that in a few minutes. But can we roll the next video, and I'll talk a little bit about what we did. So this is at a football pitch in Indiana. We put a transmitter about 100 meters apart, and we have 3 receivers on the other end. One is Rectana that's receiving energy and turning it into light so you can see it, because as an invisible technology, it's very hard to prove that you're doing anything. And this is my co-founder, Dr. Tate, but we have a number of other receivers. But one of the key things they're asking, hey, what happens when a plane flies through it? Well, we put this drone right in the middle of that power beam, and it's carrying a receiving antenna that lights up LEDs. And that's some of my team, but that's the transmitter there on the left. It's 2 meters high, 2 meters wide, about 6,400 elements. We transmitted about 60 watts to the far end in DC power. So that system is the first one anyone's ever done, and that is an actual fractional space solar power system. That is 1 satellite and 1 receiver at full scale of what we're going to do. But when you get to the other end, you need to turn it back on electricity. This is my senior scientist, Lin Ching, and this is the very system we got operational in January. These receivers that turn microwaves back on electricity are the most efficient ones ever built, at 81% efficient. That's our first attempt, and we think we can get that to high 90s. So the key to making this work is we can use existing launch vehicles. The Falcon 9 series here has transporter missions that fly about once a month, and they put a bunch of small satellites up, in maybe 15 to 20 of them. You can rent a spot on the front of the ESPA ring and their payload fairing for about $5 million. That's really cheap compared to the $60 to $66 million that the current launch costs cost, and you can put up experiments. And we intend to fly a fully operational pilot plant in 3 years by end of 2026 so that we can build the full scale system, which is just many more of the same satellites, which are about 1.5 meters across, by the end of this decade. And so if I can have Pablos come back out, we're going to show you how all of this works. So you can see on my left here, this is a transmitter. This is 1% of what I demonstrated in March of this year. And this, just no funny business. You can see there's a power supply on the ground. And so there's an LED powering this guy. I don't know if you can see it from this angle, but at scaled physics distance, so orbit to the ground, 2.5 meters is how far 35,000 kilometers is. So we talk about scaled orbital distance, the aperture size, in this case 192 millimeters squared divided by the wavelength, which is 30 millimeters, is only 2.5 meters. And we're moving power from here to here. But the fun thing is Pablos can walk all the way across the stage.
We should have made the light aim that way.
Yeah. That is actually all the way to the moon. And we're moving power the same way. So
it's actually cool because you can see, like, it's, hopefully you guys can see, it's lit up.
Yeah.
If I'm here, but if I get out of the beam, then it goes off and comes on.
Yeah.
If I'm aligned, and I guess if I got to aim it in the right direction.
Yeah, yeah. And if you hold still, this piece of paper is opaque to light, right? So if I put it in front, a little bit attenuation here. But if you put a conductor, like my tinfoil here, it blocks it completely. So if you're in a satellite or in a plane, or you're working on the ground, working on one of these microwave receiving systems, you're not exposed at all. Even though we're running fractions of the intensity of sunlight, these systems are completely safe. I've spent 60 or 70 hours standing in a power beam that's floor to ceiling. So this one's, yeah, it's fine. I mean, I would argue, I mean, you can barely tell it's on. It's like if you stand in front of your oven from across the room after taking cookies out, you're like, I can feel a little bit of the heat. And it's photons. It's the same photons that sunlight's bringing down from the sky, and we're just using a different wavelength. And it turns into heat when it intersects with your body. And one of the reasons we've built it this way is because it's safe. None of the plants or animals that are going to, I mean, we're mostly worried about birds sitting on our transmitters as they're going from north to south. during their migration periods, and getting in the way of us receiving power, but it's not going to hurt them. It's just one of those things that we want to make sure that if our goal is prosperity, really we want to make sure that everyone is going to have a good time and not have to worry about us installing big orbital death rays, which is the other option. But having said all that, hopefully you guys got a feel for what space solar power is all about. And as a commercial business, I intend to have this all done in a very short period of time because investors want to see things happen. And the technology is really ready. It's actually been possible since 2018 to do this economically. And one of the key things that you may not realize is that because all of this can be mass manufactured, and one of the key points of our architecture is we're making millions of the same thing, the same satellite over and over and over again, and they're about the cost of a laptop, a few $100s. You can build that and pay it back in just 2 years, roughly, from the investment. And that makes the levelized cost of energy, which is what you pay. I don't know if you look at your electricity bill, but I pay about $220 a megawatt hour living in a place in Michigan where the power plants have been there for 60 years. They should be paid for. So most of the cost is actually the transmission cost. But our system, by the time we build the first gigawatt, is about $30 a megawatt hour, which undercuts energy costs across the board. That's not just electricity. That is fossil fuels, the petroleum you put in your car, the aviation fuel you use to fly an aircraft. All those energy sources are more expensive than what this technology makes possible. So that is what I want to communicate, is that it's possible now. And I'm the first commercial entity pursuing this, but there's at least a half dozen others, and we hope there are more because we think the time is now.
Well, thanks. That's amazing. I have a few questions for you. And I think I don't know if we have someone with a mic, but we can also take questions from the audience. I think you covered this, but just to make it clear, like if the antenna is beaming power down to a receiver on the ground, and I decide to have a picnic on the receiver, what's going to happen?
Well, you're going to decide that you had to climb that fence to get in the middle of the receiver, but absolutely nothing. The human thermoregulatory response, and in my case it's called sweat, is able to reject a whole lot of energy, and it's only coming down as heat.
Yeah.
And this system is maximum about half the intensity of sunlight. So if you can stand to go outside on a day like today, you can stand there and maybe sweat a little bit, but that's it. That's all that's going to happen to you.
Yeah. Amazing. And so birds can fly through it, planes can fly through it, all that. We know that's working.
Yeah.
And then what about, when you talk about the launch cost coming down, if I remember right, the space shuttle was kind of $20,000 to $40,000 a kilogram to get things into space. And then SpaceX is at about $2,700 a kilogram right now, which is an extraordinary improvement. Mm-hmm. And then where's the target for this to make it sort of cost effective?
Yeah, so the Falcon 9, the earlier rocket that started in 2011, is about $2,700 a kilo to low Earth orbit. Oh. A Falcon Heavy that came out in 2018, which is about 3 times the payload, but only 50% more cost, gets you down to about $1,800 a kilo.
Okay.
At that price point, I can sell electricity for about $100 a megawatt hour. So not as cheap as all forms of energy, but these forthcoming heavy launch vehicles like Starship, its stated price point, and this is not me saying it, this is Elon saying it, is $200 a kilo. At $200 a kilo, my price is $30 a megawatt hour. And that's assuming very modest reuses of these launch vehicles. So that, again, that system, that Starship vehicle is designed for 200 launches. I'm only accounting for like 15. So amortizing the purchase of a new vehicle, reusing it 15 times. So if you get to 200, I am much lower than that.
So at 200, you basically become the lowest cost base load energy anywhere on Earth.
Anywhere ever, yeah.
And I think to me, one of the most exciting things about it is you don't need storage. Like that chart that John showed at the beginning showing how like in the winter the solar doesn't really work, that's the people working on terrestrial solar are fantasizing about having giant batteries to store energy until winter. And we don't have a technology that can do that, not at a grid scale. So it's exciting. What I think is amazing about this is it eliminates the need for storage. And you solve transmission for free too, because the other big problem we have is we're putting solar farms out in the desert and then trying to move the energy through power transmission lines to where the people are. And there's a huge amount of losses in that. And so you solve that problem too. It's just very exciting, elegant solution. So.
Yeah. And it's all enabled by modern software as well. These systems are vast distributed networks. They're all operating a lot like your cell phones are. In fact, the antennas that you have in your cell phone are microwaves as well, and they just happen to have a much smaller number of antennas than I've shown you here. This is 64 antennas, so 1% of the 6,400 that we showed earlier. But the underlying technology, the software to control all of it, is all here today. So
cool.
We have these systems are software defined, right? You can tell a transmitter to send power to 5 or 6 or 10 places at once. But hey, there's questions.
Yeah, we'll take those.
Many questions. It's fantastic.
Hi, I'm David Buda, Chair of London Futurists. Great talk.
Thank you.
Back in June, one of the cabinet ministers in the UK, Grant Shapps, announced that the UK government was going to put £4 million into support for space-based solar. Mm-hmm. Are you welcoming that? Are you part of that initiative?
Yeah,
or are you
actually we are part of the Space Energy Initiative here in the UK. We are operating under a government contract through the Net Zero and Energy Security Bureau, which was formed earlier this year. We are developing open source software tools so academia, industry, governments can model what these things look like through the University of Bristol. So yeah, we're already involved in that. We have a subsidiary based here in London so that we can leverage all the interest. So yeah, we're already taking part in that. So
awesome.
Thank you for that. Thank you for asking.
Congratulations, John. Very interesting presentation. I have been following space-based solar power for over 20 years with Keith Henson that you mentioned. And now China and Japan are also pushing for this, and these are the governments of China and the government of Japan. So how do you see them? Because you are not a government, you are a startup, and China is big, and Japan is big, and they want this technology too. So how do you see these two markets, Japan and China?
Well, I would argue that the reason startups exist is because the existing systems aren't delivering, and delivering at the cost that we like to. So as a commercial entity, I'm very motivated, and I think our timescales, even compared to all the other research organizations that have been working on this for the last 40 years, they've been saying 2040, maybe 2050, they'll get the first one up. I'm saying 2030. So not super worried about those other organizations because they just don't act like startups, and startups have an impetus to get these things delivered quickly and serving the customer's needs. So if we were to somehow run afoul of these governments, I still think the world's free enough that organizations like mine can operate and deliver what customers want. Because we make the world a better place. One of the things that we talk about, I told you we have a 12-hour orbit in that video. So that means for every asset that's in orbit, there's a ground station in the Western Hemisphere and a ground station in the Eastern Hemisphere, and they're sharing. So if you don't like the person in the Western Hemisphere, you're tied to them. It's a force for peace because your neighbor or someone else is actually sharing the energy, from someone else on the other side of the planet. So in that way, I hope that everyone would agree that this is the thing to do.
A fantastic talk, very interesting. From a practical point of view, how big would a ground station have to be to power London, for example?
Well, that is a very good question. I don't know off the top of my head how many gigawatts you use, but generally a gigawatt is 150,000 people's energy, and that's every bit of it, whether you're using petrol or diesel or what have you. I would probably guess somewhere in the 5 to 6 gigawatt range would be three ground stations, 3 2-kilometer ground stations would be necessary to power the metropolitan London area. And you can use the existing distribution infrastructure, but a lot of our initial power stations are going to be adjacent to existing solar farms, and we can use their transmission distribution equipment at night. So that you'll build up a power line, and it's only used during the day for a conventional solar, so we can build adjacent and use that at night to power. So it's a good question. Thank you.
Good morning.
Morning.
First of all, I love the idea. Congratulations.
Thank you.
Incredible. I just have a question about what is going to be a potential question that you're going to be asked. So they're talking about putting things in in space to block out the rays of the sun to slow down global warming and to slow down the heating of the atmosphere. What is the danger, since you've described that this feels like heat, of having these all around in space and coming down onto receivers, of actually warming the atmosphere?
Good question. So just in terms of blocking sunlight, these orbits are mostly above and below the path from sunlight to the ground. So we're intercepting energy above the orbit of the Earth, and we're delivering it to the ground. But the key is that I don't have the number off the top of my head, but I think it's in the terms of terawatts, the number of watts that sun projects onto the ground. And our systems are small enough that they're about 1,000th of a degree arc width above us, so you can't see it, and it's not blocking the sun because it's out of the path. So these systems are only adding fractions, small fractions, 1,000th% of additional energy to the ground compared to what the sun is already doing. And one of the key things about the sunlight that comes into the ground and warms the planet is that most of it is re-radiated away at nighttime. So if you look at your temperature profiles over the course of the evening, just before the sun rises is generally when it's coolest, and that's infrared radiation. You're rejecting all that heat that comes in. But the key element is, even if we were to increase our consumption of energy by bringing additional sunlight down, it's way less than the heat energy that's being released by fossil fuels today. So we're net dropping the energy being introduced into our atmosphere by a lot. So
Awesome.
Yeah.
Last
one.
question.
Very good.
Yeah.
All right. It's incredible. Really, really cool. So you talked a little bit about the size of like a solar array to receive the energy that would be required to power a city like London. And you talked about utilizing the infrastructure that's already built into solar farms in order to try to power that. But you talked earlier about transmission costs being much lower utilizing this kind of wireless transmission. If you're utilizing the transmission infrastructure that's already being utilized by solar energy, don't you sort of lose some of that and end up taking on those same transmission costs that's suffered by those institutions?
No. And the short answer is that you'll read about the cost to add the distribution networks, the transmission networks, to integrate intermittent renewables into our power grid. And I think globally it's a $21 trillion bill to add the infrastructure, just the transmission infrastructure, to move the energy from where it's generated to where it's being used. So that's cross-country, high-voltage DC networks and all those other things. So the key element is like there is a project you might have heard of. They're going to use put a solar farm in Morocco and run an undersea cable 3,800 kilometers here to England. And that was a $4 billion project just to build a cable. That cable is unnecessary in a situation where you're using space-based solar, because you're redirecting the energy from orbit to wherever the local use case is. And in America, most of the sun and wind is on the coasts and in the southern parts. And in order to get that to where the consumers are, you have to build a huge distribution network. And those are the costs that we're avoiding. Yeah. So that is really what we're talking about. It's not the local distribution costs, but the long-distance distribution costs. Okay, that was it, I think.
Yeah. Thanks, you guys. Thanks so much, John. This is exciting. I'm really glad we get to share it with everyone.
So let's bring on Leo.
Yeah. Great.
All right, thank you. Thank you very much.